Hello everyone. Today we are going to see how to map write and read calls to our device driver routines. Okay. Mapping write and read calls to good morning driver routines. Okay. So we do it like this. In the application, you make a write call like this. You have file descriptor is equal to write call and there are three arguments. A file descriptor, it returns, not file descriptor, sorry, the write returns number of bytes successfully written. It takes file descriptor as argument, it takes the buffer as argument, and it takes count, which is the number of bytes to write, as arguments. So these are the three arguments that are written when you make a write call, and you have been making a write call since beginning. In device driver, you have corresponding routine where the return type is signed, size type, return type, some variable. So you will give some name to your write driver routine. Suppose you give name write dev, and the arguments will be corresponding to file descriptor, which connects to stream. So there will be a stream representation device driver called stream representation kernel data structure called struct file. After that you have a buffer, so there will be constant underscore user space pointer to a buffer, followed by there is count, so there will be signed size type variable, say count, or let's call it size, and finally there will be a long offset type pointer, which I'll tell you later what is this. Now this is some ubuff, which is a pointer. This is how the write will be implemented. So the file descriptor will correspond to struct file, the buffer will correspond to constant underscore user space buffer, and the count will correspond to the number of bytes to write. What is returned by the write dev here becomes available as a return value in the write routine. Okay, this is how the write will be implemented. First we will implement the write routine. So the goal is to make our operations reach the device. The device could be connected to your system in two ways. One of the two ways in which the device could be connected is that the device is connected to the driver, and the driver is a driver stack connecting to a port driver, which is further connected to machine, or the device could be directly connected through the driver to the machine. So two ways are port and the device, or directly the device. Now this is what we have already done. We have written an application in which we have given open and release calls. The open and release calls map to the underlying device driver. Yes, please. Huh. No, the serial port or the parallel port or the USB port or the Ethernet port. Um, yeah, I mean those IO ports. That are mounted on the motherboard. Like you have your RAM slot or VGA slot, not VGA card, VGA slot. Just see this application in which there is some data to be written. You have already performed open on your device, and you have successfully opened your device by running your own open routine. That has already been done till now. Okay, and you have done same thing for release also. Now we have to move on and we have to do it for write. Okay, we'll have some hardware, some device on which we have to perform some writing. That hardware will be accessible across the kernel. The kernel interacts with the external world through the kernel buffers, which are IO buffers, also famously known as dirty buffers. Above this red line, which consider it to be VFS. Okay, above this you have application. Application have some data that has to be written down to your device. Now, application will give the write system call. The write system call will normally maps to some routines, but it will here in your case map to your driver routine. Inside your device driver routine, you will initiate data transfer using some macro, which I'll tell you now. Very first thing we have to do is you have to give a write call from the application and map it to our write driver routine instead of the default routine, the default write routine given in the kernel, which is capable of writing into some files inside the disk. We will take control to our device driver routine, where we will implement our own algorithm. Okay, so let's move on. Here we are. Application first, in which I can see that we have already implemented the write device.c. Let's have a look at it. So this is our write device.c that we have created the write function, but we have not yet done anything in this. If you look at your open device function, your open device function creates a file descriptor and returns the file descriptor back to main menu. The main menu gets the file descriptor in the form of ARG from the open routine and further returns it back to main. So it is in main, here it is. Okay. File descriptor, which is again passed as argument and goes back to main menu. And the main menu captures the file descriptor, which is a valid file descriptor this time, and passes this valid file descriptor to the open routine. Sorry, to the write routine. Now you go to write dev. So in write dev, here you have valid file descriptor. So very first thing to do is you extract the file descriptor out of this, like this. File descriptor is equal to arg, which is a void pointer. Typecast this void pointer into integer pointer and then fetch the value out of this integer. Now you have the file descriptor ready. Using this file descriptor, you will perform a write. Return is equal to write. Using this file descriptor, write this buffer of this length. Okay, so we have to declare these variables, return length, and you have to have this buffer also. Let's have this buffer of type char. Let's put some data also in this. Let's say we put an EmbLogic slogan, innovation driven by intelligence and logic. We'll write this. Okay, then length, we have to find the length of this before you write. Length of this is equal to string length of buffer. So we have length also, and we will perform writing. The write return value has to be checked. If the return value is equal to -1, this is some error. Generated from write call, simple application, and we'll call the exit function. Did we implement the exit function? Yeah, we did. So we'll call the exit function. What is the exit function number? Somebody know this? Okay, good. Star FPTR function number 1, and the exit is a failure. Okay, due to whatever reasons, we'll typecast it to void star. Okay, so this is how we will implement the write. Otherwise, we'll say wrote %d bytes successfully. Okay, so this is the simple write operation. Okay, application is done. Let's go to the file operations, struct file operations. Yeah, yeah, we have to pass RT. Here it is, RT passed. Then in the file operations, we had to map the write system call with the corresponding device driver routine. That also we have done. Okay, let's go ahead and implement write driver routine. It is used in device drivers in kernel for mapping the system calls which you see in yellow with the corresponding system call routines, I mean device driver routines. Now before we put anything in the write call, write routine, let's see is it at least mapped successfully or not. Okay, so for that we will insert the driver. Now test script. Number 1, check-in. Check-in is successful. Number 2, checkout for build. Successful. Number 3, build driver. Successful. Number 4, insert driver. Insertion is done. There it is. Major number is 238. 238. and 238 major number and all minor numbers done. And then after that, driver is inserted successfully. Now number 7, test with application 7. The application is built and the new CD is created on 6th April, 238 major number, 0 minor number, and it's a C for character device. Okay, enter. Do you want to run application? Of course, yes. Now the application is running. Application menu, 1 for open device, 1. Enter. Please give the device open mode O_WR only. Enter. Please give the device name CDD150, right? Enter. Now you check what happened inside kernel. Well, here you see open dev begin, trim dev begin end because it is opened in the right mode, and open dev end. So our open routine is called successfully, which because it was opened in the write mode, further called trim. Cool enough. Now we are going to perform write 3. Enter. That's all. Let's see what happened in device Java. Oh, we did not map to the driver routine. We have made the write system call from the application, but we could not map to the driver routine. Something is not right. Something is just not right. So application exit. So there is some problem in the application. The write device routine did not get called because it would have printed a write begin. That did not happen. So let's go back to init function. Declarations function first. In declarations function we have declared write dev, read dev, okay. Init.c. Write is not mentioned here. The write number of functions also increase to 6. Okay, that's fine. So we have to initialize the write device function. Function number 4. Write device. No, we'll decide that. We'll check in the main menu. How do you happen? Write is 3 and read is 4. Okay. So application is done. So let's redo the application. And when we go to the main menu, now the write system, write function will be called. Here we are back in the application. Test with application number 7 once again. Oh, it says in main you can't assign it with -1 because it's a pointer. So we had this problem earlier also. Let's fix this problem. FD is a pointer, it will be null. Not -1. Let's test with application number 7 once again. Now it's okay. Application build failed. Undefined reference to write device. Okay. Go back to application and see there is a make file. Inside make file we have not mentioned a write device in application. .o. write device.o, write device, write device, write device mentioned now. So let's test once again. 7, test with application. Application build appears to be successful this time. Yeah, it's done. So 238 is the major number. Application built successfully. Do you want to run application? Yes. Okay, 1 for open device. Give the device open mode o_wr only. Give the device name cdd150. Done. Now 3 for write. Okay. Still write did not happen. Exit application. Go back to applications. Scan the application properly from the beginning. Declarations.h. Write and read. Write device is declared as a generic function. In the init, write device is declared and the write device is initialized. Function number 4. Here we give choice 3. So 3 plus 1 4, function number 4 is invoked. This is invoked correctly. I don't see any flaw in here. Let's go to the write routine. So this is the write dev, where we are performing write. Yeah. Equal to hai, so it should work. Less than equal to 2 hai. It will be 4. Correct, Ayush. So now it will be invoked. Test application, test number 7. Number 7, test with application. Okay, application built successfully. Do you want to run app? Yes. 1 open device o_wr only. Please give the device name to open. This is cdd150. Okay. Now number 3, we will open, write the device. Enter. There it is. Wrote 0 bytes successfully. So write application is being called. Write driver routine is being called now. See, write dev begin and write dev end. So this is a beginning of big things. We will know how to write. See, your device could be CD-ROM, it could be DVD, it could be Blu-ray, it could be magnetic tape, it could be some USB port, Ethernet port. So different things. It could be some printer, thermal printer, laser printer, dot matrix printer, inkjet printer. It could be any type of printer. So how you will write on those devices, you have to decide, isn't it? So therefore, every device driver will have its own different type of write routine. Suppose you have a touch screen device driver, how will you write there? So things are different, for every device. So we have to implement write dev. In the device driver routine that we have implemented, we have returned 0. So whatever will be returned from write routine will go to the return value of write. Yeah. Huh. Huh. That's correct. So what's your query on this? नहीं तो ऐसे ऑटोमेटिक नहीं हुआ। राइट से पहले मैंने ओपन किया था, तो फाइल नेम क्या दिया था? फाइल नेम मैंने cd 150। वो cd 150 बनाई कैसे थी? नो, फाइल सिस्टम में बनी थी, MK नोट करके बनाई थी, isn't it? तो MK नोट करके जब बनाई थी तो उसमें आपने मेजर नंबर माइनर नंबर भी दिया था। तो उस मेजर नंबर माइनर नंबर, बिकॉज ऑफ द प्रेजेंस ऑफ दैट मेजर नंबर एंड माइनर नंबर, it was understood that this is not an ordinary storage file in secondary storage. It was understood because of the presence of the major and minor number, it was understood that this is a device file and there is a device driver for it. And the device driver is listed in the device table with the major number 238 in our case. So control went to the device driver. Struct file operations. Inside struct file operation is saw that the write system call has a mapping to the write routine called write dev. So control went to write dev, not the ordinary system call routine of the kernel. So we have done the close device, and after that we do exit application. And then we are in the device. Here we remove the device driver, number 5, remove driver 5, 238 gone. And then finally we exit the script by giving number 0, exit the script. We are back to driver. Okay, let's do one more thing in the application before we proceed further. In the application we have written a generic function for read device also. Let's go to init and implement a function for, declare a function for read device also. Initialize this function pointer for read device. Then go to the read device function. No, first you go to main menu function. Inside main menu function, change this number to 4. Yeah, it's fine. Now go to read device function. Inside the read device function, you will have to give the read call. Okay, this we'll see later. Let's come back to write. This is what I told you that the write function, write driver routine that you will implement will look like. Write method performs copying data from application down to your device driver, hardware device actually. The prototype looks like this. The first argument is a pointer to struct file. You remember I told you struct file is a stream representation kernel data structure. Constant char underscore user buffer. Okay, this has a special meaning, I'll tell you. This is the count, which was the third argument of the write call. Third argument of your write call, which was count. Okay, this resembles the number of bytes that you're going to write. Okay, about this buffer. Now this is a special buffer. Okay. The presence of __ user here explains us that this particular pointer is going to point to user space buffer, some buffer in user space. Which buffer in user space? Well, that you have specified using write system call. So this __ user space buffer will point to a buffer array in the user space. Okay, as specified by __ user macro, it will refer to a user space buffer. Also notice that it has been made constant. The contents of this user space buffer are not updated during the data transfer from app to device. Why is it made constant? The user space buffer. This buffer is made constant by the driver during the data transfer. Because the count has been established that how many bytes from this buffer will be copied in this buffer to the kernel space. Now because it has been specified, this buffer should not be modified by some other application thread during the data transfer, during the execution of write routine. So therefore, this buffer is made constant for that duration for which the data transfer will happen from the application to the kernel space. The contents of the user space buffer are not updated, therefore they are made constant during the data transfer, during the execution of write from app to device. Okay, this is long offset type. I'll talk about this later. The return value is whatever you want to return. It should be actually the number of bytes written successfully brought successfully from the application to the kernel space buffer. That is the number of bytes should be returned, or you can return -1 on error. So this is how it looks like. This strut file is the strut file which represents the stream. This is constant char __ user space buffer, which refers to some user space buffer. This is the count, is the number of bytes to write in the application, from the application to the device, and this is the long offset type pointer, which we'll discuss later. Data has to move from the application buffer to the kernel buffer. Now it is possible that the application developer has given this buffer as an argument which contains some data that has to be written down to user space buffer. But suppose the application developer have not allocated this buffer properly. I mean, the memory is not allocated for this buffer. This is a pointer to the buffer, but the memory is not allocated to the buffer. This is a flaw, isn't it? So how is it resolved? The driver will have a invalid pointer in this case, because it will be pointing to the user space buffer as specified by __ user. So it will be pointing to the user space buffer, but if the buffer is not allocated properly, then what will happen is this pointer will be pointing to an invalid buffer, and when it will try to move data from this invalid buffer down to kernel space, well, in application layer it will get a segmentation fault and the application will crash. In the kernel layer, this will also be invalid access and the kernel will crash. So we have to prevent it. __ user. The user space pointer may not be valid while running in kernel mode. This user space pointer may not be valid. Maybe the memory is not allocated yet. There may be no mapping for the mentioned address. The application have not allocated memory. It could point to some random data. Application have a dangling pointer, or maybe null. The user space memory is paged, or maybe the application developer have allocated a page. Fine. Let's have a look at this scenario. Now the application developer have used the write call which points to a buffer. And the buffer is created like this. Buffer is allocated like this, in which there is some data. And this buffer is stored in user space memory. The user space memory is divided in pages. So many pages. So many pages. All the pages are in memory. It may be possible that if the buffer was not used for some time before the read write call happened, there is a possibility that this buffer could move, the page could move to swap space. Page out. The user space application developer created this buffer successfully. Memory was allocated properly. Data was stored in there. But then nothing was done for a while. So CPU thought that okay, maybe this page is not being used, and moved this page to the page out, moved to the swap space using page out mechanism. So this page, which was containing some buffer, which was containing some data, was unnecessarily occupying so much space in memory. So the intelligent CPU memory management mechanism moved this page to the swap space and made memory available. Now the application makes a write call and the driver's write routine runs, and when the driver's write routine runs, the driver's write routine uses this pointer to refer to the user space buffer, which the application is happy that our application have created this buffer successfully. But when it comes to using this buffer, the page is unfortunately paged out to swap space. So again the fault could happen even after doing everything correctly. So the user space memory is paged. The memory is in question might be paged out and not resident in RAM when the system call was made. So attempting to refer the user space memory directly could generate a page fault. So therefore the page fault will return in a page fault and a oops message, lot of WPS oops message, which result in the death of the user space process and the corresponding kernel thread, which is your device driver. Okay. Also, accessing this, using this pointer, you can access the user space buffer directly. So don't you think that the kernel becomes very vulnerable? It becomes very easy for somebody to crash the kernel. It provides an open doorway, allowing a user space program to access or overwrite memory anywhere in the system and maybe make it crash. Okay. So therefore, though this particular pointer underscore user space pointer is provided, fine, but you will still not be, you should not use this pointer directly. Okay. So how to use this pointer in the write routine, that we will see in the next class tomorrow. Okay. If you have any queries, you can ask me now.